Welcome to the lecture. My name is Sonain Jamil and registration number 16T16. Today we will discuss what are filter basics, analog versus digital filters, how information is represented in signals, time domain parameters of digital filter, frequency domain parameters, high pass, band reject filters. So, what are the basics of filters? Digital filters are used for two general purposes. The first one is signal separation. When two signals are combined, the digital filter is used to separate both signals. And the other purpose is signal restoration. Let's see the examples in the book. Signal separation is needed, the sky highlighted. Signal separation is needed when a signal has been contaminated with interference. For example, imagine a device measuring the electrical activity of baby's heart while still in womb. The raw signal will likely be corrupted by breathing and heartbeat of the mother. A filter might be used to separate these two signals. Now, signal separation is used when a signal has been distorted in some way. For example, an audio recorder made with poor equipment may be filtered to better represent the sound as it actually occurred. Another example is the deblurring of image. Okay. The next thing is analog versus digital filters. Analog filters are very cheap as compared to digital filters. They are fast, have large dynamic range in amplitude and frequency, but digital filters are superior in level of performance. They have better performance than analog filters. Now, how information is represented in signals? There are two ways to represent information in signals. The first one is time domain, and the other one is frequency domain. In time domain, we have three parameters that we should check whether to design a filter with a good response or not. So to have a better performance, a filter should have fast step response, no overshoot. It should have linear phase. Let me show you. The first one, this one, is slow step response. This means this filter will have very poor performance as compared to the second one, which has the fast step response. It is good than the previous one. The second thing that I talked is overshoot. The first one having overshoot there, as you can see that there is the overshoot. So this filter will have poor performance as compared to the second one, that is with no overshoot. This is better than the first one. The third thing is the linear phase. As you can see that in the left side, this phase, if we draw tangent over there, this phase is very different to this phase. While if we talk about linear phase and we draw tangent over the two changes on the right side, it will have same phase as in the both cases. The first one is non-linear phase, it will have poor performance, while in the second case it has linear phase, it will have a better performance than this one. Now, frequency domain parameters. There are three frequency domain parameters. To design a good filter, a filter with better response and good performance, we should have fast roll off, flat passband, and good stop band attenuation. Let's see. As the first one has very slow roll off, while the second graph shows that the filter has very fast roll off. So the second one has better performance and is good than the first one. Ripples in passband attenuation. As I talked, there should be flat passband. As you can see that this is the passband and there is the ripples in the passband. This filter will have poor performance as compared to the second one, which has very flat passband. The passband is the band or frequencies where the filter allows signal to be passed. So the the third parameter in frequency domain is stop band attenuation. To design a good performance filter, there should be good stop band attenuations rather than poor stop band attenuation. As you can see that in the first case we have a filter which has very poor stop band attenuations, while in the second case it should have a good stop band attenuation, which means that the second filter is better than first filter. So different filters, there are different types of filter. Low pass filters, as you can see that I discussed earlier, this is the pass band, the filter allowing the frequencies to pass. This is the transition band, convergence of pass band to stop band. Between both of them there is a region which is called transition band, and then the filter blocks the frequencies and that region is known as stop band. There are different types of filters: low pass filter, high pass filter. Low pass filter allows low frequencies to pass and high frequencies to stop. There is a cutoff frequency, after that the filter stops the frequency or blocks the frequency. In high pass, this filter blocks low frequencies and allows the high frequencies to pass. There is pass band. This filter allows a band of frequency to pass and block all other frequencies. Band reject. This filter does reverse to the band pass filter and rejects only the desired band of frequencies and allow all the frequencies to pass from the filter. So let's see from the book some of the things. This is the impulse response. Now if we talk about the filters, the impulse response of a filter is known as filter kernel. Scientists call it as filter kernel. There is the impulse response of the filter and frequency response. Then we talked about how Information is represented in signals. Time domain parameters, frequency domain parameters. Now, how can we design a high pass filter from a low pass filter? This is the filter. As you can see that this is the original filter kernel in time domain, and that is the frequency domain, and we want to design the C filter kernel with spectral inversion. From this, what we will have to do is just flip top for the bottom. We just flip this and slide it. Then we talked about high pass, band pass filters, and as you can see that how we can generate a high pass filter by using low pass filter, and we can only generate by subtracting a low pass filter from all pass filter. What it will do, it will stop all the low frequencies and allow the high frequencies to pass. Now if we want, this will happen. If we want to design a band pass filter from low pass and high pass filters, if we have a low pass filter, we can design all the filters, all other filters. All other filters are derivatives of low pass filter. As you can see that we designed a high pass filter from low pass filter. Now we are going to design a band pass filter by using low pass and high pass filter. If we convolve both low pass and high pass filters, a band pass filter will be the result of both. Now if we want to design a band reject filter, we will just have to add a low pass filter with a high pass filter. That's it for today's lecture. Thanks very much for watching.